Let's review from part 1 of this video that for any polynomial f of x and any complex number k, there exists a unique polynomial q of x and number r such that f of x equals x minus k times q of x plus r. Note that this equality is true for all complex values of x. Let's find f of k. So we need to substitute x with k. We get f of k equals k minus k times q of k plus r. This factor is k minus k or 0, so f of k will equal r. This proves the following remainder theorem. If the polynomial f of x is divided by x minus k, then the remainder is equal to f of k. This theorem gives a new method of evaluating polynomial functions. As an example, we use the remainder theorem and synthetic division to find f of k for the following function when k equals 5. Instead of replacing x by 5 to find f of 5, we divide f of x by x minus k, or in this case x minus 5. K is 5, and now we have to bring down the coefficient of x squared. The coefficient of the x term is minus 4, and the numerical term is just 5. Now we move down 1. 5 times 1 is 5. Minus 4 plus 5 is 1. 5 times 1 is 5. 5 plus 5 is 10. So there's a remainder from this division. The last number is the remainder. It's 10. Because of the remainder theorem, we know that f of k equals r. In our case, f of 5 is 10. That's how we can use synthetic division to evaluate functions. We can check to make sure that the value of the function is the same using the other method. We'll replace f of x by 5 and you get f of 5 equals 5 to the second power minus 4 times x plus 5, or 25 plus 530 minus 20, exactly 10. We get the same value for f of 5. Next example. Use the remainder theorem and synthetic division to find f of k for this function f of x when k is 3. We divide f of x by x minus 3 using synthetic division. 2 is the coefficient of x to the 5th. X to the 4th is missing, so we have to write 0. Then negative 10, the coefficient of x to the 3rd. Negative 19 of x squared. The x term is missing, so we write here 0 and negative 50. Let's apply the synthetic division. We'll bring down 2. 3 times 2 equals 6. 6 plus 0 is 6. 3 times 6, 18. 18 minus 10 is 8. 3 times 8, 24. Minus 19, 5. 3 times 5, 15. Plus 0, 15. 3 times 15, 45. Minus 15, negative 5. So negative 5 is the remainder of dividing the function by x minus 3. We know from the remainder theorem that f of 3 is negative 5. f of k equals to the remainder of dividing by x minus k. This is a different method to evaluate the function. The other way is just to substitute x with 3, and you see that lots of evaluating will be involved because you have to raise 3 to the 5th power, then to the 3rd, multiply many times, synthetic division is a simpler method to evaluate functions. Now let's see the following example. F of x is x to the second minus x plus 3, but k, note that k is a complex number. The work will be similar to the previous two problems, except that we have to deal with complex numbers. First, we write the value of k, it is 3 minus 2i. Then let's bring down the coefficients. 1, negative 1, and 3. I'll bring down 1 here. I have to multiply k by 1. 3 minus 2i times 1 will be 3 minus 2i. Now we have to add the two numbers in the second column. We add the real parts. 3 minus 1 is just 2, and minus 2i. Now we have to multiply k by this number. We'll do the work on the side. The easiest way to do the work is to think that I is a variable and to follow the two binomials. So I get the product of the first two terms. 3 times 2, 6. Outer terms, minus 6i. Inner terms, minus 4i. Last terms, negative 2i times negative 2i will be 4i squared. But I is the imaginary unit, so its square is negative 1. We replace here I squared with negative 1. And then 4 times negative 1 is negative 4 plus 6, 2. Minus 6i minus 4i is minus 10i. This is the result of multiplying 3 minus 2i by 2 minus 2i. We have to write it right here. 2 minus 10i. And now we have to add the numbers in this column. 3 plus 2, 5 minus 10i. And this is the remainder of dividing f of x by x minus 3 plus 2i. So, using the remainder theorem, we can state that f of k, and it is 3 minus 2i, is equal to 5 minus 10i. Now we'll see how to test potential zeros. What is this zero of a polynomial function? It is the value of the variable that zeros this function. Here's the definition. A zero of a polynomial function f is a number k such that f of k equals 0. That's why the name is 0, because this value zeros the function. But you know that if you want to find the x-intercepts of a given function, you have to let y be 0 or solve the equation f of x equals 0. So the real number zeros are the x-intercepts of the graph of the function. But if k is the 0 of the function, then it will make it 0. So if we substitute here x with k, we see that the remainder must equal 0, because the function must be 0. So we can use synthetic division to find f of k, and if the remainder is 0, then f of k will equal 0, and k will be a 0 of the function. By the way, a 0 of a function is also called the root or solution of the equation f of x equals 0. Let's apply the method for the following example. Use synthetic division to decide whether the given number k is 0 of the given polynomial function. If it's not, give the value of f of k. F of x is this function and k is negative 3. So I have to use synthetic division to find f of k. If it's 0, if the remainder is 0, then k k will be 0 of the function. If not, it's not a 0. Take the coefficients of the x terms, 1, 2, negative 1, and 6. K is negative 3. Bring down 1, multiply negative 3 by 1. Result is negative 3. Negative 3 plus 2 is negative 1. Multiply negative 3 by negative 1. 3. Minus 1, 2. Then negative 3 times 2 is negative 6. Plus 6, 0. So the remainder is 0. This means that f of negative 3 will equal 0. It's the same as the remainder. So negative 3 is a value that makes the function 0. So it is a 0 of this function. Negative 3 is a real number, so this is also the x-intercept of the function. Or on the side I can write the coordinates of the x-intercept. Negative 3, 0.